In this video, we're covering the cross product. So recall that there are two types of vector multiplication. The first one was the dot product, and the second one now is the cross product. So whereas the dot product of two vectors yields a scalar value, so scalar again, it's just a constant. So it's basically a number like 6, 7, minus 3, 100. The cross product of two vectors now is going to yield another vector. So the dot product gave us a scalar, and the cross product now is going to give us a vector. Note that the cross product is only defined for three-dimensional vectors. So you can't calculate a cross product, for example, with two-dimensional vectors, for example, 2 and 3, and then another vector would be 5 and 6. So it doesn't work on two-dimensional vectors. It has to be three-dimensional. Whereas the dot product, that worked with two-dimensional vectors, and you could also calculate dot product for three-dimensional vectors. So the cross product of two vectors, we have vector A and there are its components. So A1, A2, and A3, and vector B, there's its components, B1, B2, and B3. And it's defined as follows. So the cross product of A and B is equal to, now there is a formula for the cross product, but that formula is conveniently expressed in terms of a 3 by 3 determinant for the cross product. So we have a 3 by 3 determinant, and you have to work this out. You are going to use, most of the time, you're going to use cofactor expansion along the first row. So how do we get this matrix, or this 3 by 3 matrix, and then calculate the determinant? So in the first row, we're going to have the standard basis vectors I, j, and k. In the second row, we're going to have the components of the first vector that is appearing in this cross product, and that's A. And I'm making a point of stating that in the second row, you have the components of the first vector, because you'll find out later that cross product between B and A, so I'm just going to say B times A instead of cross product all the time. B times A is very different from A times B. Okay, so there is a difference. The order is important, basically. And in the last row, you'll have the components of your second vector. So that's how you're going to calculate the cross product. And I'll show you how to do the cofactor expansion in some upcoming examples. So why is the cross product so special? Why are we bothering actually learning about this? So the cross product, so A times B, it's a vector. And this is a vector that is perpendicular to both vector A and vector B. So if you look at it in terms of a diagram, here's vector A, here's vector B. Don't worry about the theta right now, it's just in this drawing. We'll come to it later. So here's vector A, here's vector B. You can see that AB here is in red, and it is at a 90-degree angle to vector A and at a 90-degree angle to vector B. So we say that the cross product A times B is perpendicular. Another word for perpendicular in this case is orthogonal. So it's perpendicular or orthogonal to vector A and vector B. All right, exercise 1. So we're going to calculate the cross product of A and B, and then we'll calculate B times A. So notice that there is a difference in order. You'll have to calculate these two. And here are your vectors A and B. And then I want you to check at the end whether A times B is the same as B times A. All right, let's do this example. So we'll work out A times B, and that's equal to the determinant of the 3 by 3 matrix. In your first row, you're going to have I, second row J, third row vector K. In the second row, you're going to have the components of vector A, so that's 2, 7, and minus 9. Then in the third row, we're going to have the components of vector B, so that's 1, minus 3, and 2. Now what we're going to do is use cofactor expansion along the first row. Okay, so we're going to look at that I, J, and K, and you'll generally always do this. So this is equal to, now when we're doing cofactor expansion, remember one of the first things we need to do is account for the checkerboard matrix. So it's going to be positive 1 times vector I, so that's just going to be vector I, and then we're going to get the determinant of the submatrix. So cross out column 1 and row 1, and there is your submatrix. So it's 7, minus 9, minus 3, and 2. It's going to be minus j because, again, account for your checkerboard matrix. It'll be minus 1 times j, that's just minus j. And then your submatrix, let's get that out of the way. The submatrix is going to be 2, 2, 1, and minus 9. Then we're going to have plus vector k plus 1 times vector k, and the submatrix is 2, 7, 1, minus 3. Now let's work out the determinants of the 2 by 2 matrices. All right, so it's 7 times 2, that's 14, and then it's going to be minus 3, minus 9 is 27, so it's 14 minus 27, minus j into 2 times 2 is 4, 1 times minus 9 is minus 9, so it's 4 minus minus 9, that's 4 plus 9. Then we have plus vector k, 2 times minus 3 is minus 6, and then we have 1 times 7, that's 7, so it's minus 6, minus 7, that is just going to be minus 13. Let's work this out. 14 minus 27, that's minus 13 times vector I. 4 plus 9, that's going to be 13 times a minus. We have minus 13j, and then we have minus 13k. So by pure coincidence, all of these components are minus 13. So this is equal to minus 13, minus 13, and minus 13. There we go. So this here is the cross product of A times B. So it's A times B. Let's work out what B times A is. Okay, so this is B times A. The only thing that's going to change here is the components. So in the second row, you're going to have the components of your first vector. First vector is B, so it's 1, minus 3, and 2. And then we're going to have the components of A, so it's 2, 7, and minus 9. All right, let's get to the subvectors, or basically cofactor expansion. So again, it's plus 1 times by I, that's just going to be I, and then the determinant of the submatrix, that's going to be minus 3, minus 9, 2, and 7. Then we have that minus j again, a part of cofactor expansion. Submatrix is 1, minus 9, 2, and 2. Then we have plus positive k, submatrix is 1, minus 3, 2, and 7. All right, let's work out these determinants. So that's minus 3 times minus 9, 27, minus 2 times 7, so that's 27 minus 14, that's positive 13, right? 1 times minus 9 is minus 9, 2 times 2 is 4, minus 9 minus 4, that's minus 13, plus vector k into 1 times 7 is 7, 2 times minus 3 is minus 6, 7 minus minus 6, that's 7 plus 6, that's 13. So we're going to get 13i, and then double negative, so that becomes plus 13j plus 13 vector k. And this is equal to 13, 13, and 13. Now this is B times A, and A times B was equal to minus 13, minus 13, minus 13. Can you see that when I swap the order, so here it's A times B, here it's B times A, the only thing that changed between these vectors is that I basically multiplied them by a negative. So when I went from here to here, I took this vector and multiplied it by a negative 1, and vice versa. If you want to go from here to here, you take that vector and you will multiply it by negative 1 to get this vector here, minus 13, minus 13, minus 13. And that's one of the properties of the cross product that you will see. So I'll just give you a prelude to it now. One of the properties is that A times B is equal to the negative of B times A, right? You just swap the order and you put a negative sign in front of it. All right, exercise 2. Again, calculate b times a and exercise 2. Again, calculate a times b and b times a, and you have your vectors a and b. Then I want you to verify if a times b is equal to b times a, and if that's not the case, what's the relationship? All right, let's do this example. So let's work out vector a times vector b. That's equal to the determinant of the 3 by 3 matrix. First row, that's the I, j, and k standard basis vectors. Second row, it's going to be the components of A2, minus 3, and 4. Last row, components of B, 1, 0, and 8. All right, let's use cofactor expansion along the first row. So accounting for the checkerboard matrix, let's put that in there. It's going to be plus, minus, plus. So it's always plus the I vector minus the j vector plus the k vector. Okay, and the determinant of the submatrix will be minus 3, 4, 0, and 8 minus the j vector and submatrix 2, 1, 4, and 8. Okay, then we're going to add the k vector and we will account for the submatrix. So it is going to be 2, minus 3, 1, and 0. All right, let's work out the determinants. So it'll be vector I into minus 3 times 24, minus 3 times 8, that's minus 24. And then we have 0 times 4, that's 0, so we don't have to worry about it. Then we have 2 times 8, 16, minus 4 times 1, which is 4, so it's 16 minus 4, that is going to be 12. Then we have plus k into 2 times 0 is 0, then it's going to be 1 times minus 3, which is minus 3. But it's 0 minus minus 3, so double negative, it's going to be plus 3. So it's going to be minus 24i minus 12j plus 3 times the vector k. So it's going to be minus 24. By the way, you can leave your answer like this if you want to. I just like writing it out in terms of the components. Okay, there we go. So it's minus 24, minus 12, and 3. That's the cross product for A times B. Now, knowing what you know from exercise 1, what do you expect B times A to be? Do we expect it to be that? No, we don't, not exactly. What we expect it to be is, let's multiply this by a negative. We expect B times A to be 24, 12, and negative 3. That's what we expect for B times A. Let's check if we are correct. Okay, so what I'm going to do is I'm going to take out these 2 by 2 determinants, and I'm just going to get the new 3 by 3. So what we'll have is no longer A times B, it will be B times A. So your 3 by 3 matrix now will be 1, 0, 8 in the second row and 2, minus 3, and 4 in the last row. Okay, so it will be I times, what's the submatrix? Now it's 0, 4, 8, minus 3. Now for J, okay, so take out that, we'll have 1, 2, 8, and 4. Okay, and then the last one will be 1, 0, 2, and minus 3. Let us work out that doesn't look like a K. I just noticed that. There we go. All right, let's work out the determinants for the 2 by 2 matrices. 0 times 4, that's 0. And then it's going to be minus 3 times 8, minus 24. So it's 0 minus minus 24. That's plus 24, double negative. Minus j into 1 times 4 is 4. 2 times 8 is 16. 4 minus 16, that's minus 12. Okay, plus the k vector into 1 times minus 3 is minus 3. 2 times 0, we don't have to worry about that, it's 0. So we're just going to have minus 3 here. This is going to give us 24 times standard basis vector I plus, so double negative, 12j minus 3k. And is it as we expected, 24, positive 12, and negative 3? Yes, it is. Okay, so that is the vector b times a. Again, we are seeing, and this is a property of the cross product, a times b is equal to minus b times a. There we go.